Terraforming Mars, science or fantasy? For all of human history, Mars has been a red light in the sky, glowing quietly in the darkness, watching us. Ancient civilizations believed it was a god of war because of its blood-like color. Today, we know it as a cold desert world covered in dust and ice, with a sky tinted pink instead of blue. But in the modern age, Mars has become something else entirely. It is no longer just a distant planet. It is a question, I challenge, a dream. Can we transform Mars into a world like Earth? Can we terraform an entire planet? Terraforming means changing a planet's environment to make it more like Earth. The word sounds like science fiction. It brings to mind giant machines melting ice caps, building oceans, and planting forests under alien skies. For decades, this idea lived mostly in books and movies. But today, scientists study it seriously. Engineers run simulations. Private space companies make plans to send humans there. What was once fantasy is now discussed in research papers and space agency meetings. Mars is the most Earth-like planet in our solar system. It has a day just a little longer than ours, 24 hours and 37 minutes. It has seasons because it tilts on its axis. It has polar ice caps made of water and frozen carbon dioxide. There is clear evidence that billions of years ago, rivers once flowed across its surface. There were lakes, possibly even oceans. Mars was not always the frozen desert we see today, but something changed. Mars lost most of its atmosphere. Without a thick atmosphere, the planet could not trap heat. Temperatures dropped. Water froze or escaped into space. Today, the average temperature on Mars is about -80 degrees Fahrenheit. That is colder than Antarctica. The atmosphere is about 100 times thinner than Earth's and is made mostly of carbon dioxide. There is almost no oxygen. If you stood on Mars without a spacesuit, you would lose consciousness in seconds. So if Mars is so hostile, why even consider terraforming it? The answer is simple. Compared to every other planet we know, Mars is the least impossible. Venus is far too hot, with temperatures hot enough to melt lead. The outer planets are gas giants with no solid surface. Their moons are intriguing but extremely far away and deeply frozen. Mars, while harsh, is within reach. It is a world we might be able to change. The first step in terraforming Mars would be warming it up. Right now, it is too cold for stable liquid water. But Mars already has greenhouse gases, especially carbon dioxide, trapped in its ice caps and soil. If we could release enough of that carbon dioxide into the atmosphere, it could thicken the air and trap heat, warming the planet through a greenhouse effect similar to what happens on Earth. Some ideas sound almost unbelievable. One proposal suggests placing giant mirrors in orbit around Mars to reflect sunlight onto the polar ice caps. The extra heat would cause frozen carbon dioxide to evaporate, thickening the atmosphere. Another idea involves darkening the surface of the ice caps with dust so they absorb more sunlight. Some scientists have even suggested redirecting ammonia-rich asteroids toward Mars to add greenhouse gases and heat. But here is where science pushes back against imagination. Recent studies suggest Mars may not have enough accessible carbon dioxide stored in its ice and soil to create a thick, warm atmosphere. Even if we released everything available, it might only raise the atmospheric pressure to a small fraction of Earth's. That would still be too thin for humans to breathe and too thin to keep the planet warm long term. Another major obstacle is radiation. Unlike Earth, Mars does not have a strong global magnetic field. Earth's magnetic field acts like a shield, deflecting harmful solar radiation and cosmic rays. Without that protection, astronauts on Mars would be exposed to dangerous levels of radiation. Some scientists have proposed creating an artificial magnetic shield in space between Mars and the Sun. In theory, it could deflect solar wind and help protect a thicker atmosphere. But building such a structure would be one of the largest engineering projects in human history. Even if we solved the temperature and radiation problems, gravity presents another challenge. Mars has only about 38% of Earth's gravity. We do not fully understand what living long-term in lower gravity would do to the human body. Would bones grow differently? Would children born on Mars develop normally? These are questions we cannot yet answer. Then there is the issue of water and soil. Mars has water ice, especially near its poles and underground. If the planet warmed, some of that ice could melt, forming rivers and shallow seas. But Martian soil contains toxic chemicals called perchlorates. Before crops could grow safely, the soil would need treatment. Scientists are already experimenting with simulated Martian soil on Earth to see what plants might survive. And what about oxygen? Humans cannot breathe carbon dioxide. Producing a breathable atmosphere would require converting massive amounts of carbon dioxide into oxygen. On Earth, plants and algae do this through photosynthesis, but covering Mars with enough plant life to create a thick oxygen-rich atmosphere could take thousands of years. Before any of this happens, humans must first reach Mars and survive there. A journey to Mars would take 6 to 9 months using current technology. Communication delays could stretch up to 24 minutes one way. Astronauts would have to make decisions without immediate help from Earth. Early settlers would likely live in pressurized habitats, possibly underground or inside lava tubes for radiation protection. Water would be mined from ice deposits. Oxygen could be extracted from water or even directly from the carbon dioxide in the atmosphere. Fuel for rockets could be manufactured on Mars itself, reducing the need to carry everything from Earth. This concept, known as in situ resource utilization, would be essential for long-term settlement. Colonization, however, is not the same as terraforming. Colonization means building controlled habitats where humans survive with technology. Terraforming means reshaping the entire planet so humans could one day walk outside without a pressure suit. Colonization may happen within this century. Terraforming, if it happens at all, would likely take many centuries. The scale of transformation required is enormous. We would need energy on a planetary level. Vast solar farms or nuclear reactors might power factories producing artificial greenhouse gases. Industrial centers on Mars would have to operate continuously for decades or longer to slowly alter the climate. Every step would require careful monitoring. Planetary climate systems are complex, and small changes can lead to unexpected results. There are also ethical questions. What if Mars contains microbial life deep underground? If we terraform the planet, we could destroy a second example of life in the universe before fully understanding it. Do we have the right to reshape an entire world? Economics also plays a critical role. Launch costs must continue to drop. Reusable rocket technology developed by companies like SpaceX is helping lower the cost of access to space. Space agencies such as NASA are planning long-term missions that aim to establish a sustained presence beyond Earth. International cooperation, similar to what made the International Space Station possible, would be required on an even larger scale. Terraforming Mars is not impossible according to the laws of physics, but it demands patience measured in centuries, resources measured on planetary scales, and unity measured across civilizations. The people who begin such a project would never see its completion. They would be working for a future they will never experience. So is terraforming Mars science or fantasy? It is science in theory. It is fantasy in terms of our current abilities. It sits on the boundary between what we can imagine and what we can achieve. Perhaps centuries from now, humans will look up at a thicker Martian sky and see clouds drifting where none drift today. Perhaps rivers will flow again across ancient valleys. Or perhaps Mars will remain a cold desert visited only by research stations and small settlements. For now, the red planet waits. Cold, silent, unchanged, waiting for the first permanent footsteps. Waiting to see whether humanity chooses to simply visit or to transform. And even if we succeed in turning Mars into a second home, we would still be bound to one star, because beyond Mars lies an even greater challenge: the journey to the stars themselves. Interstellar travel is warp drive possible for thousands of years. The stars have inspired wonder. Ancient people looked up at the night sky and saw patterns, myths, and gods. Today, we look up and see something even more powerful. We see destinations. Mars is close. Even at its farthest, it is still part of our solar system, but the nearest star beyond our sun is unimaginably distant. The closest one is Proxima Centauri, a small red star located about 4.24 light-years away. A light-year is the distance light travels in 1 year. Light moves at about 186,000 miles per second. That means Proxima Centauri is roughly 25 trillion miles away. To understand how far that is, imagine traveling there with one of the fastest spacecraft ever built. The Parker Solar Probe, launched by NASA, can reach speeds of about 430,000 miles per hour at its fastest. That is incredibly fast by human standards. But even at that speed, it would take more than 6,000 years to reach Proxima Centauri. 6,000 years. Longer than recorded human history. With our current technology, interstellar travel is not just difficult. It is practically impossible within a human lifetime. The distances are simply too vast. So when people talk about traveling to other stars, they are usually imagining something far more advanced than chemical rockets. They are imagining revolutionary propulsion systems, breakthrough physics, or something even more extreme. They are imagining warp drive. Warp drive became famous through science fiction, especially shows like Star Trek. In these stories, starships travel faster than light by warping space itself. The ship does not move through space in the normal way. Instead, space in front of it is compressed, and space behind it is expanded. The ship rides inside a bubble of distorted space-time. It sounds like pure fantasy, but surprisingly, the idea has roots in real physics. In 1994, physicist Miguel Alcubierre proposed a theoretical model based on Einstein's theory of general relativity. According to Einstein, space and time are not fixed. They can bend and stretch. Massive objects like stars and planets curve space around them. Gravity is not just a force pulling objects together. It is the result of curved space-time. If space-time can bend naturally, could it be bent artificially? The Alcubierre model suggested that it might be possible to create a warp bubble by contracting space in front of a spacecraft and expanding space behind it. Inside the bubble, the spacecraft itself would not be moving faster than light. Instead, space itself would be moving. This is important because Einstein's laws say that nothing can travel through space faster than light, but they do not forbid space itself from expanding or contracting faster than light. In fact, the universe is already expanding. Distant galaxies are moving away from us faster than the speed of light because the space between them is stretching. So in theory, a warp drive does not break the laws of physics. But there is a catch. The biggest problem is energy. The original model required an enormous amount of energy, more energy than exists in the observable universe. Later refinements reduced that estimate, but it is still far beyond anything humanity could generate. Some versions require exotic matter with negative energy density, something that may not exist in usable amounts. Negative energy appears in tiny quantities in certain quantum experiments, but controlling it on a large scale is far beyond our capabilities. So while warp drive is not forbidden by physics, it may be forbidden by practicality. If warp drive remains out of reach, what other options do we have? One idea is nuclear propulsion. Instead of burning chemical fuel, a spacecraft could use nuclear reactions for thrust. Nuclear thermal rockets would heat hydrogen using a reactor and expel it at high speeds. Nuclear pulse propulsion, once studied during the Cold War, would involve detonating small nuclear explosions behind a spacecraft and riding the shockwaves forward. The physics is sound. Such systems could potentially reach a significant fraction of the speed of light. Another idea is laser propulsion. Imagine a lightweight spacecraft attached to a large reflective sail. Powerful lasers based on Earth would fire at the sail, pushing it forward using light itself. Because the spacecraft would not need to carry heavy fuel, it could accelerate to very high speeds. Some proposals aim to send tiny probes to nearby stars at about 20% of the speed of light. Even at that speed, a journey to Proxima Centauri would take more than 20 years. That is within a human lifetime, but traveling at such speeds introduces new dangers. At a fraction of light speed, even a tiny grain of dust becomes deadly. A collision could release enormous energy. Shielding would need to be extremely strong. Navigation would have to be nearly perfect. And then there is the problem of slowing down. It is not enough to reach another star. You must also stop. Relativity introduces another fascinating effect, time dilation. As an object approaches the speed of light, time slows down for it compared to observers at rest. If a spacecraft traveled at 99% of light speed toward a star 100 light-years away, Earth would measure the journey as taking over 100 years. But for the travelers, time would pass much more slowly. They might experience only a few years during the trip. In this way, humans could theoretically reach distant stars within their own lifetimes while centuries pass on Earth. But achieving 99% of light speed would require unimaginable energy. The faster you go, the more energy you need. This creates what engineers call the tyranny of the rocket equation. More fuel adds more mass. More mass requires more fuel. The cycle quickly becomes impractical. Matter-antimatter propulsion is another theoretical possibility. When matter meets antimatter, they annihilate each other and release huge amounts of energy. Even a small amount could power a spacecraft to incredible speeds. But antimatter is extremely rare and difficult to store. We can produce only tinier amounts in particle accelerators, and at enormous cost. Then there is the idea of the wormhole, a shortcut through space-time. Imagine folding a piece of paper so two distant points touch. A wormhole would connect two distant regions of space with a tunnel, allowing near-instant travel. Like warp drive, wormholes are allowed by the mathematics of general relativity. But keeping one open would require exotic matter with negative energy, and we have no evidence that stable wormholes exist. Even if we discovered one, controlling it would be another challenge entirely. Perhaps instead of sending humans first, we send machines. Robotic probes powered by advanced artificial intelligence could explore distant star systems and transmit data back to Earth. In many ways, our machines may reach the stars before we do. Human travel, however, introduces biological challenges. Even on the International Space Station, astronauts experience bone loss, muscle weakening, and vision changes after months in microgravity. A journey lasting decades would require artificial gravity, likely created by rotating parts of a spacecraft. Radiation is another major threat. Outside Earth's protective magnetic field, cosmic rays constantly bombard spacecraft. Over years, this radiation increases cancer risk and damages electronics. Shielding adds mass, which again increases fuel requirements. Then there is the psychological challenge. Imagine leaving Earth forever, watching the sun shrink into just another star, living in a confined environment with the same small group of people for decades. The emotional strain could be immense, and yet humans have always crossed frontiers. When earlier explorers sailed across oceans, they did not know what they would find. When astronauts rode rockets into orbit, the risks were enormous. Curiosity and ambition drove them forward. Interstellar travel would be the greatest frontier of all. Warp drive remains theoretical, a mathematical possibility. Some small research efforts continue exploring whether space-time distortions could one day be engineered, but no one has built a warp engine. No experiment has demonstrated faster than light travel. It is possible that new discoveries in physics could reshape our understanding of what is possible. Before Einstein, relativity was unknown. Before quantum mechanics, atoms were mysterious. Science evolves. Limits shift, but it is also possible that the speed of light is an absolute boundary built into the structure of reality. If that is true, humanity's expansion into the galaxy will be slow. It will take generations. We may become a species that plants seeds of civilization among the stars, one system at a time. Warp drive captures our imagination because it promises instant connection across unimaginable distances. It promises that no star is too far away, but even without it, the dream of reaching the stars remains alive. The universe contains hundreds of billions of stars in our galaxy alone. Many of them have planets. Some may have oceans. Some may have life. The question is not whether the stars are there. The question is whether we will ever reach them. If we do, the night sky will no longer be the distant display of unreachable lights. It will be a map of places we can go, and if we ever master interstellar travel, we will no longer be confined to one solar system. We will become a galactic species, but before we can cross the gulf between stars, there is still much to build closer to home, because reaching other worlds requires structures larger than anything humanity has ever created, structures that stretch thousands of miles into space. The next step in our journey is not about speed. It is about building bigger than we ever have before. Space elevators and megastructures. For as long as humans have built civilizations, we have built upward. From ancient pyramids to modern skyscrapers, height has always symbolized ambition. But what if we did not stop at the clouds? What if we built a structure that stretched all the way into space? The idea sounds impossible at first. Rockets are how we reach orbit. They roar with fire and burn enormous amounts of fuel just to escape Earth's gravity. Every launch costs millions of dollars. Every kilogram sent to space is expensive. Rockets are powerful but inefficient. A single rocket launch can burn through hundreds of tons of fuel, create massive sound waves, and produce dangerous exhaust. Even reusable rockets, like those developed by SpaceX, are impressive but still limited by cost and payload size. Now imagine something very different. Imagine a cable stretching from the surface of Earth all the way up into space, one end anchored to the planet, the other extending beyond geostationary orbit. Along this cable, electric-powered climbers slowly carry cargo and passengers into orbit without rockets. No explosive launches, no massive fuel tanks, just a steady ascent into the sky. This is the concept of the space elevator. The idea dates back more than a century. In 1895, Russian scientist Konstantin Tsiolkovsky imagined a tower reaching into space after seeing the Eiffel Tower. Later, scientists realized that instead of building upward from the ground, it might be possible to hang a cable down from orbit. It was a brilliant insight. Instead of pushing upward against gravity, the structure could hang under tension, using centrifugal force from Earth's rotation to stay tall. Here is how it would work. Earth rotates once every 24 hours. At a certain height above the equator, about 22,236 miles, an object in orbit moves around Earth at the same speed Earth rotates. This is called geostationary orbit. A satellite placed there appears to hover above the same spot on Earth. If a long cable were anchored at Earth's equator and extended past geostationary orbit, centrifugal force from Earth's rotation would keep the cable stretched tight. The upper part of the cable would act like a counterweight, pulling outward, while gravity pulls the lower part downward. The result would be a stable structure held in tension. Climbers could move up and down this cable using electric motors powered by lasers or solar energy. Cargo could be delivered to orbit far more cheaply than with rockets. Some estimates suggest the cost per kilogram could drop from tens of thousands of dollars to mere hundreds. Imagine satellites, space telescopes, or even whole space stations delivered along this cable steadily and safely, like elevators in a skyscraper. If built, a space elevator would revolutionize space travel. It could open the door to permanent human presence in orbit. Science experiments, manufacturing, energy collection, and even tourism could all become feasible at unprecedented scales. But there is one enormous problem: materials. The cable of a space elevator would need to be unbelievably strong and lightweight. Steel is far too heavy. Even the strongest conventional materials would snap under their own weight long before reaching space. For decades, no known material could handle the stress required. Then scientists discovered carbon nanotubes, tiny cylindrical structures made of carbon atoms. In theory, carbon nanotubes are incredibly strong, far stronger than steel at a fraction of the weight. On paper, they seemed perfect for a space elevator cable. Single strands could theoretically hold millions of times their weight in tension, but producing them in long, flawless lengths is another challenge entirely. Even a tiny defect could trigger catastrophic failure. Currently, we can produce nanotubes only in short segments, and weaving them into a continuous cable tens of thousands of miles long is still science fiction. Beyond material challenges, there are environmental hurdles. A space elevator must survive lightning strikes, hurricanes, and temperature fluctuations on Earth. Once above the atmosphere, it must withstand impacts from micrometeorites, orbital debris, and even solar storms. Even a small collision could damage or sever the cable. Shielding the structure against these threats adds weight and complexity. And there are geopolitical concerns. A structure stretching into space would be one of the most critical pieces of infrastructure in human history. Who would control it? How would it be defended? What if it were sabotaged during a conflict? The risks are enormous, but so are the potential rewards. Some engineers propose building a space elevator on the moon first. The moon has weaker gravity, which reduces the stress on the cable. It also has no atmosphere, which eliminates weather concerns, and fewer micrometeorites. A lunar elevator could transport materials from the moon's surface into lunar orbit, providing building blocks for larger space projects. Once we imagine building structures that large, our thinking expands. Consider the idea of orbital habitats. These would be massive rotating space stations, spinning to create artificial gravity through centrifugal force. Inside, people could walk, farm crops, and build entire communities. Some designs envision cylinders miles long with artificial landscapes along the inside surface. Mirrors would direct sunlight into these habitats, allowing plants to grow and rivers to flow. Such structures could orbit Earth, Mars, or even float freely in deep space. In theory, they could house millions of people. And then there are the largest concepts of all, megastructures. One famous idea is the Dyson sphere, proposed by physicist Freeman Dyson. A Dyson sphere is not necessarily a solid shell surrounding a star, as often imagined in science fiction. Instead, it could be a swarm of solar-collecting satellites orbiting a star, capturing a significant portion of its energy output. The sun emits more energy in a single second than humanity has used in all of history. A Dyson swarm could harness this energy to power civilizations on a galactic scale. Other proposed megastructures include ring worlds, massive rotating habitats encircling stars, and space-based solar power arrays that beam energy back to Earth. While these concepts are far beyond current technology, physics allows them. They force us to think beyond our planet, beyond even the moon and Mars, toward a future where humanity uses the resources of the entire solar system. Mining asteroids becomes essential in this context. Asteroids contain metals, rare elements, and water resources that could fuel space habitats and megastructures. The moon also holds valuable materials. Energy from the sun constantly bathes space, mostly unused. A civilization capable of building megastructures would harness these resources on an industrial scale. Megastructures also bring risks. Large structures in space could fail catastrophically, disrupt orbital environments, or become strategic targets in conflicts. Their construction would require coordination and technology on a level humanity has never achieved before, but history shows that humans thrive on bold infrastructure projects. Railroads, power grids, and the internet transformed civilization. Space elevators and orbital megastructures could do the same for humanity in space. Building at this scale is about more than size. It is about capability. It transforms space from a distant frontier into a realm of human activity. Once we can lift materials reliably into orbit, harvest energy efficiently, and construct habitats beyond Earth, we can begin reshaping our solar system. We can terraform planets, assemble interstellar missions, and create permanent, self-sustaining human settlements in space. Megastructures are not just dreams. They are stepping stones toward a future where humanity is no longer confined by gravity, where space is filled with life, industry, and civilization. And to achieve that future, we must first reach out to the richest resources in our solar system, the metals, minerals, and water locked in asteroids, moons, and comets. The next chapter of our journey begins with mining the riches of space itself. Mining asteroids for resources. The vastness of space is filled with untapped riches. For centuries, humans have looked at the night sky and wondered what lies beyond. Today, our curiosity has a practical edge. Space is not just empty, it is full of raw materials, metals, minerals, water that could transform life on Earth and enable humanity to expand across the solar system. Mining asteroids is no longer just a concept in science fiction. It is the next frontier for exploration, industry, and survival. Asteroids are rocky and metallic remnants from the formation of the solar system. They vary in size from tiny boulders to objects hundreds of miles across. Some orbit the Sun between Mars and Jupiter in the asteroid belt, while others, called near-Earth objects, occasionally pass close to our planet. Each asteroid is a capsule of resources frozen in time, containing metals like iron, nickel, and cobalt, precious metals like platinum and gold, and even water trapped as ice. Water is particularly valuable. In space, water is more than a drink or a habitat necessity, it is fuel. Hydrogen and oxygen can be separated from water and used to create rocket fuel. A single icy asteroid could support countless missions deeper into the solar system without ever having to lift fuel from Earth. Mining water from space eliminates the cost of launching enormous quantities of fuel from the surface, which is currently one of the biggest barriers to large-scale space exploration. The idea of asteroid mining is not new. In the 1970s, scientists first proposed sending spacecraft to capture and process asteroids. Back then, it seemed impossible. Technology was too limited. But in recent decades, advances in robotics, propulsion, and autonomous systems have brought the concept closer to reality. Asteroid types and case studies. Asteroids come in many varieties, each offering different opportunities and challenges. Scientists classify them broadly into three types: carbonaceous C-type, silicate S-type, and metallic M-type. C-type asteroids are rich in water, carbon, and organic compounds. They are essential for sustaining life in space, providing water for drinking and oxygen production, as well as the raw materials to create fuel. Notable examples include Bennu and Ryugu, visited by NASA OSIRIS-REx and JAXA Hayabusa 2, respectively. Both missions return samples to Earth, giving scientists a precise understanding of the water and organic content of these bodies. S-type asteroids contain magnesium, silicon, and iron. These are harder and more metallic, ideal for construction and manufacturing in orbit. Eros, visited by NASA near Shoemaker mission, is an S-type asteroid that gave scientists insight into surface conditions and the challenges of anchoring mining equipment. M-type asteroids contain high concentrations of iron, nickel, and rare platinum group metals. 16 Psyche, a massive metallic asteroid roughly 140 miles in diameter, is one of the most promising mining targets in the solar system. Estimates suggest its total metal content could be worth tens of trillions of dollars. Mining an asteroid like Psyche would provide both raw materials for space construction and advanced metals for Earth industries. Robotic mining concepts. Mining asteroids presents engineering challenges unlike anything on Earth. Many asteroids spin rapidly, some tumble unpredictably, and others are rubble piles, loose collections of rocks held together by gravity. Anchoring equipment to these bodies is far more complex than placing drills on Earth. Anchoring methods proposed include harpoons or claws that grip the asteroid's surface, magnetic tethers for metallic bodies, inflatable shells to contain debris during extraction, adhesives or suction systems for small or porous asteroids. Robotic miners would perform nearly all operations. They would operate autonomously or semi-autonomously, coordinated through artificial intelligence. Swarms of drones could drill, cut, melt, and transport material for metallic asteroids. Concentrated solar energy or microwave systems could melt metals, which are then shaped into usable forms for construction. For icy, carbon-rich asteroids, heating elements could vaporize water, which would be condensed and stored for fuel or life support. Robotic swarms offer redundancy and efficiency. If one unit fails, others continue working. They could also self-repair or replicate basic components using 3D printing, creating a semi-autonomous industrial ecosystem on the asteroid. Orbital refineries and industrial workflows. Extracting raw material is only the first step. To maximize efficiency, processing in orbit is essential. Large orbital refineries could melt metals and refine them into beams, plates, or other components, purify water, splitting it into hydrogen and oxygen for fuel, produce basic construction materials using 3D printing, assemble components into modules for space stations or interplanetary spacecraft. Processing in orbit avoids the enormous cost of returning raw materials to Earth. It also enables continuous operation, supporting human expansion throughout the solar system. Water extracted from asteroids could fuel spacecraft traveling to the Moon, Mars, or beyond, while metals provide the backbone for orbital habitats, space elevators, and megastructures. Economic considerations. The economics of asteroid mining are staggering. A single metallic asteroid could contain hundreds of tons of platinum, worth trillions of dollars. Yet transporting these metals back to Earth is likely inefficient. The greatest value lies in using resources in space, reducing the cost of construction, fuel, and life support. Estimates suggest that orbital refineries and mining operations could eventually reduce the cost of sending materials into space by orders of magnitude. Water for fuel, metals for construction, and organics for life support become the foundation of a space-based economy. In time, asteroid mining could reduce the cost of every mission, making human expansion into the solar system far more feasible. Timeline for implementation. A realistic roadmap for asteroid mining spans decades. 2020's prospecting missions, sample collection, and testing of robotic technologies. Missions like OSIRIS-REx and Hayabusa 2 provide data on asteroid composition. 2030's small-scale robotic extraction and orbital refineries could become operational. Water and metals could be processed and used to fuel lunar and Mars missions. 2040's, 2050's fully autonomous mining colonies could operate continuously, providing industrial capacity in orbit. This stage enables the construction of permanent habitats and supports interplanetary travel. Governance and societal implications. Asteroid mining raises legal, ethical, and geopolitical questions. Space resources are a shared heritage of humanity. International treaties must regulate ownership and property rights, liability for accidents or miscalculations, environmental impacts in space, equitable distribution of resources to avoid monopolization by a few nations or corporations. The United Nations Office for Outer Space Affairs and other international organizations have begun discussions, but as asteroid mining moves from theory to practice, new policies will be essential. Cooperation will be key. Mismanagement could lead to conflicts over valuable resources, collisions, or orbital debris hazards. Philosophical and strategic significance. Mining asteroids is more than a technical challenge. It represents humanity's first tangible step toward becoming a solar system civilization. Every asteroid mined, every orbital refinery launched, and every fuel depot constructed brings us closer to a future where humans live and thrive beyond Earth. Asteroid mining is the bridge between imagination and reality. It transforms the dream of permanent human presence in space into a practical plan. By tapping into the solar system's resources, humanity gains the foundation for space elevators and orbital habitats, interplanetary spacecraft and fuel depots, megastructures and energy collection systems. Asteroids are stepping stones that transform our civilization from earthbound to spacefaring. They allow us to build, innovate, and prepare for the challenges of living among the stars. Mining asteroids is not just about wealth or survival, it is about expansion, exploration, and capability. Once asteroid resources are fully harnessed, the solar system itself becomes a connected network of opportunities, enabling life, industry, and civilization to grow far beyond Earth. The next chapter in this journey is about what we can build with the materials we have extracted, a story that will lead directly into permanent human habitats in orbit and on other worlds. Terraforming Mars, science or fantasy? Mars has always captured human imagination. Its red deserts, towering volcanoes, and frozen poles make it seem both familiar and alien. For centuries, people have dreamed of walking on its surface, planting human flags, and perhaps even living there. But dreams are one thing, making Mars habitable for humans is an entirely different challenge. The concept of terraforming, or transforming Mars into a world that can support human life, is both awe-inspiring and controversial. Can we realistically make Mars a second home for humanity, or is it just science fiction? The first thing to understand is what makes Mars so hostile. Its atmosphere is extremely thin, less than 1% of Earth's pressure, made mostly of carbon dioxide, with almost no oxygen. Temperatures are bitterly cold, averaging about minus 60 degrees Celsius, with nighttime dips far lower. Mars lacks a global magnetic field, leaving its surface exposed to cosmic radiation and solar winds. Water exists mostly as ice, and liquid water is rare on the surface. In short, humans cannot breathe, drink, or survive on Mars without advanced technology. Terraforming aims to change these conditions, step by step, to make Mars more Earth-like. There are three main goals for terraforming: thickening the atmosphere to increase surface pressure and trap heat, warming the planet to melt ice and create liquid water, and introducing oxygen and nitrogen to create a breathable environment for humans and Earth-based life. Warming Mars. One of the first challenges is increasing the planet's temperature. Mars is cold because it is farther from the Sun and its thin atmosphere traps very little heat. Scientists have proposed several ways to warm the planet, introducing gases such as carbon dioxide, methane, or engineered fluorocarbons to trap heat in the atmosphere, using large orbital mirrors to reflect sunlight onto the surface, or redirecting small asteroids rich in ammonia to collide with Mars, releasing heat and gases. Each method has advantages and disadvantages, with greenhouse gases working slowly, mirrors requiring immense engineering, and asteroid impacts being risky. Thickening the atmosphere. Mars' thin atmosphere means humans cannot survive on the surface without pressure suits. To make the planet habitable, the atmosphere must be thickened. Carbon dioxide trapped in the polar ice caps and soil could be released through warming. Volcanic activity, either natural or artificially induced, could also release gases. A thicker atmosphere would support human life and help trap heat and melt water ice. Yet Mars lacks a magnetic field, so solar winds slowly strip away gases, meaning continuous replenishment is necessary. Introducing oxygen. Once the planet is warmer and the pressure higher, oxygen must be added. Plants and algae could produce oxygen through photosynthesis, gradually altering the atmospheric composition. Genetically engineered organisms might accelerate this process. Even with optimistic estimates, reaching breathable oxygen levels could take hundreds or thousands of years. Early habitats or domed cities provide controlled environments while terraforming progresses. Energy and infrastructure. Terraforming Mars is not just about gases, it requires enormous energy and infrastructure. factories to produce greenhouse gases, orbital mirrors, or even robots to release ice or chemicals must operate continuously for decades or centuries. Energy sources include nuclear reactors, solar arrays, or small fusion plants. Water and building materials must be extracted from the Martian surface or brought from Earth or asteroids. Asteroid mining could supply metals for construction and water for fuel, linking terraforming and space industry in a shared strategy. Biological challenges. Even if Mars' atmosphere and temperature were altered, humans face biological hurdles. Radiation from cosmic rays and solar storms remains high because Mars lacks a global magnetic field. Microbial life introduced to help terraform the planet might survive, but humans still need protection. Underground habitats or radiation shields may be required for centuries. Introducing Earth life also raises ethical questions about destroying potential Martian life. Timelines for terraforming. Terraforming Mars is a multi-century project. Initial warming and thickening of the atmosphere would take decades to centuries. Biological introduction of microbes and plants could take centuries more to produce oxygen and enrich soil. Large-scale ecosystems with forests, rivers, and potential domesticated plants and animals may take several more centuries. Partial terraforming, however, allows human habitat to expand and evolve as technology progresses. Proposed technologies. Several technologies are proposed to enable terraforming: artificial volcanoes to release gases, orbital mirrors to focus sunlight, chemical factories producing potent greenhouse gases, asteroid impacts to release heat and volatiles, and genetically engineered organisms to produce oxygen and improve soil. Each method has trade-offs in speed, cost, risk, and feasibility. Cost estimates. Terraforming Mars is astronomically expensive, with estimates ranging from trillions to tens of trillions of dollars over centuries. Energy requirements are immense, including orbital mirrors, chemical production, and asteroid redirection. Asteroid mining and orbital industries may offset some costs. Long-term investment could be justified by humanity's survival and expansion. Ethical and philosophical considerations. Terraforming raises ethical questions. Should humans alter another planet? Could life already exist on Mars, risking destruction? Does humanity have the right to reshape an entire world for survival? Terraforming requires balancing human ambition with planetary stewardship, shaping not only Mars' future but the moral framework of humanity as a spacefaring species. Cultural and psychological impacts. Early settlers face isolation, harsh environments, and long-term challenges. Mars' lower gravity, thin atmosphere, and day-night cycle require adaptation. Over time, Martian culture may develop uniquely, blending Earth traditions with innovations born from life on a new world. Robotic terraforming systems. Before humans arrive, robots will survey, build, and initiate terraforming. Survey drones map terrain and resources. Atmosphere processing machines release CO2 and other gases. Water extraction robots melt ice for fuel and life support. Construction drones build habitats, factories, and greenhouses using local materials and 3D printing. Energy systems support continuous operation with solar or nuclear power. These robotic systems lay the foundation for human arrival and large-scale terraforming. Colonization strategies. Colonization is phased. Small research stations testing habitats, life support, and greenhouse gas production. Semi-permanent colonies with agriculture, water recycling, and energy independence. Terraforming supports cities managing greenhouse gas systems and introducing life. Full colonization with open-air habitats, agriculture, and thriving ecosystems. Historical context. Mars exploration spans centuries. Telescopes, mariner missions, Viking landers, rovers like Spirit, Opportunity, Curiosity, and Perseverance, and sample return missions like OSIRIS-REx. Each mission provides knowledge to guide colonization and terraforming, life support and agriculture. Even partially terraformed Mars requires life support, controlled temperature, pressure, oxygen, nitrogen, water recycling, and waste management. Agriculture provides food and oxygen with hydroponics, aeroponics, and genetically engineered crops suited for low pressure and CO2-rich air. Contingency planning. Terraforming spans centuries, requiring backup habitats, redundant robotics, emergency plans for radiation, dust storms, or chemical imbalances, and generational continuity in knowledge and infrastructure. Engineering a thick atmosphere. Methods include releasing CO2 from polar ice caps, heating regolith to release gases, industrial greenhouse gas production, and artificial volcanoes. Maintaining a thicker atmosphere requires continuous replenishment due to solar wind stripping, producing oxygen, photosynthetic organisms, electrolysis of water, and mineral oxidation produce oxygen gradually. Reaching breathable levels could take centuries, with early settlers relying on habitats. Climate modeling and monitoring. Simulations model heat, atmospheric circulation, water cycles, and dust storms to optimize strategies. Continuous monitoring ensures adjustments to greenhouse gas levels, oxygen, and ecosystem health. Step-by-step terraforming engineering phases, robotic setup, atmospheric modification, water mobilization, biological introduction, habitat expansion, and advanced terraforming for open-air human activity. Projected settlements. Early research stations grow into semi-permanent colonies and eventually full cities with lakes, rivers, and greenery. Population scales from dozens to tens of thousands over centuries, concentrated near the equator initially, expanding to mid-latitudes later. Mars-Earth economic integration. Mars develops a new economy, exporting rare minerals and data to Earth, importing specialized machinery and expertise, and creating self-sufficient local production. Asteroid mining and orbital refineries reduce dependence on Earth, enabling a solar system-wide economy. Radiation protection. Solutions include subsurface habitats, radiation-resistant materials, water shielding, and potentially localized magnetic fields to protect human settlers from cosmic rays and solar radiation. Visionary Mars. Fully terraformed Mars may host open-air cities, lakes, rivers, greenery, sustainable agriculture, energy infrastructure, scientific hubs, and spaceports connecting Mars with Earth, the Moon, and asteroid stations. Philosophical and cultural significance. Terraforming Mars represents humanity's ambition to become multiplanetary, balancing ethical responsibility with technological innovation. It is a commitment across generations, reshaping human civilization, culture, and identity beyond Earth. Mars is more than a new home, it is a testament to human ingenuity, resilience, and imagination. It challenges us to think beyond our planet and prepares humanity to thrive among the stars.